Okay, this is unit 22B of the course Mathematical Methods for Signal Processing, and we have just discussed or verified that an element is in the support of a function or a mild distribution if you can localize the Dirac out of it by multiplying with appropriate functions. And the idea was to take very narrowly concentrated functions which are concentrating more and more around the point. So in our case, it was 0. And the proof was, because everything is Fourier invariant, through the Fourier transform and weak-star convergence was actually convergence of bigger and bigger compact sets on the Fourier domain. Now, if we just take this result and translate it, I have this corollary already mentioned, that the spectrum, Fourier spectrum, as we will call it, is not the spectrogram, but the spectrum of a mild distribution is the support of the Fourier transform, which is well defined. And so we just replace multiplying with Kn by convolving with the Gn. There's no big difference whether you are taking arbitrary elements in a 0 or just compactly supported on time or on frequency side. You should just avoid to take functions which are compactly supported on time and frequency because they don't exist. It's only the 0 function. Recall that if you have compact support on the time side, you have analytic functions on the Fourier transform side, so it's prohibiting to have compact support. Okay, so I mentioned already that this formulation tells you, well, what we're doing is we're filtering out, and in a way, we're filtering out pure frequencies. So roughly speaking, well, pure frequencies are maybe not eigenvectors with non-zero eigenvalue. So that would be the case of a bounded measure. If a bounded measure is on the Fourier transform side, mu hat of lambda is different from 0, we would say, okay, clearly the character which is sitting at this point has the eigenvalue mu hat of lambda, or s if you want. But if you're at the boundary, it's a little bit more tricky because you cannot take it and you have to take the closure of all these things. Now, Fourier analysis tries to find the frequencies in the space, in the signal in sigma. Now, Fourier synthesis tries to say, well, can we re-synthesize it? And we have already understood that weak-star convergence is the right thing to do. So the question is, well, if we are filtering out the relevant frequencies, isn't it clear that you can reconstruct the function from those frequencies? So why should you use any frequency that you cannot pull out of this signal or so? And if you think of the classical situation of functions on the torus or periodic functions, I mean, if you have Fourier coefficients as an orthonormal system, and then you're saying, well, I'm using only the coefficients which are non-zero, of course, it's still the Fourier series. You have just made changes on the labels which are 0 contribution. So that's no problem. But here we're in a more delicate situation. So it was really, I think, the motivation for very much work on these closed ideals of L1 and so on, in order to find out that, yes, it's possible in R3. This is a famous example by Laura Schwartz of an application of his ideas about distributions also, to find a distribution where the frequencies inside the distribution, so the support, is not good enough to determine the to have approximation. So if you only take trigonometric polynomials, this is what you get by finite linear combinations of relevant frequencies. With sk in the spectrum, you are not able to approximate the original one if you're kind of smart and if you're doing a very special example. I mean, we don't have to do it. It's good to know it, but we don't have to discuss it. I also wanted to mention once more that this indirect definition that I gave was recalling from Hans Reiter's book of a spectrum of an L infinity function. If you view H as an element of of a 0 prime, it's an equivalent definition. I also think it's a nice observation to say if you decompose a sigma with the help of a partition of unity, any a 0 partition of unity, so maybe triangular function or so, you can say that the support is the union of these supports. And this is because normally you would like expect a closure, but here you can say that they are living at different sets. So if you're interested in the point, then it is only touched by finitely many of these local supports. And that's why you can just take the union locally. So that means the support discussion can be reduced to discussing the support of an individual sigma psi number 5 or 20. And that's maybe sometimes helpful or so. Now, what I want to do at the end of this theoretical part is to explain to you that the distributions or mild distributions with one point support, so which are concentrated on a single point, they are just the Dirac measures. This has a lot to do with the lack of smoothness in the Fourier algebra. So if you would look at distributions, you could say, well, I take the the tempo distribution, which assigns to every Schwartz function f prime at 0, so the derivative at 0. It's like with the polynomials, we have seen a lot of functionals like second derivative at some point and all these things. They are meaningful for tempo distributions, but they are not meaningful for FL1, and that's the big thing. And I would like to explain it to you. And the lemma that I have proved the first part today is used to this. So the claim is you're saying, I have observed that there is some mild distribution which is supported on a single point. And then the first step that I would like to tell you is that whatever it is, we can choose a nice smooth partition of unity, and we can arrange such that the point that you give me is inside this. So the first part is creating such pupus which have a small plateau, which are also smooth, then they are in a 0, and that then you shift the whole system such that your point is inside, or you rescale it, and so you can have arbitrary fine partitions of unity such that you have this property. Now, the story is essentially the following, and the picture is explaining it very, very much, that you have a single K0. So this is in the picture, maybe the brown guy is number 25, and that's the only guy, and it's constant 1 a little bit nearby the value x, and all the others are 0. So kind of when the support is, you can multiply the distribution sigma with the psi k with number k0, and you will reproduce it. So that's the part that we have. Now, what we have to do also is to show that the action of such an abstract distribution, but with a very good concentration, is just a multiple of the Dirac at this point. Now again, we can shift everything to 0, so we can assume that this point is the 0 point, and therefore we are interested in two things. One is the null space. Okay, there's a symbol missing. The null space is the set of all test functions which are annihilated by this. And the claim is that this is exactly the ideal of all the functions which are vanishing at this point of interest or so. Okay, so kind of, if you would have a derivative, that would be a proper subspace. So that's the trick. Now, we use this lemma that you can approximate every function, and this was this bandpass filter, by a function h1, which is not only 0 at the point, but nearby. and with compact support, and the difference is small, so we can approximate, means we write the function h in this ideal as h1, which is the good guy, plus something which is small. So what happens if you apply such a functional on this? Well, you're getting sigma is sigma of, that's a typo, of h1 plus sigma of the difference. h1 is now something which is living on using all the guys except our brown guy. So there, it's something, a bandpass is living to the left and to the right of this, but not involving this one here because it's 0. So that means the h1, we have modified the h very little to h1, and the h1, that's a typo here, should give 0, so it's 0. Plus something which is sigma applied to something small. Now, sigma, again, another typo, sorry. Sigma of h, we take absolute values. It's at most 0, which is not written, plus the functional norm applied to the norm of this here. But this is small, therefore we get something which again is very small. So sigma of h is smaller than epsilon, sometimes some constant, but this is fixed, and this is true for every epsilon, which means that sigma of h is 0, and that means, of course, that we are in this ideal. Now, this ideal is a maximal ideal. That means you cannot enlarge it. If you add a function which has value non-zero here, you get all of S0. So every function can be split. So essentially, to make it quick, I would say the sigma has the property that if you change the input, let's say, sigma is having the same value for any two functions which are different from this by any element from I0, which means it depends, sigma as a consequence depends only on the value of your function f, because that's all that you can say. If you add arbitrary functions which have 0 value, it just means that the value is fixed, all the rest is determined. Now, you choose any f in S0, which at this point has the value 1. Then you get some number, let's call it lambda. Now, if you come with another element which doesn't have this, you can rescale it. You replace the g by, so I should probably write g over g0, and you get the function f1, and this function f1 has the value 1. Yeah, so kind of that should be a g here. So what can you say about sigma applied to g? Sigma is just sigma of, well, we rewrite g from f. We have obtained g by dividing, we obtained f1 by dividing the g, so that's the typo, by g0. So you rewrite it, f1 multiplied with g0 is clearly the f. It's the g. Okay, so it's chaos here, but I will have to correct it. But you just rescale everything. Then you get the value at 0 times lambda, which is lambda times delta 0 of g. So essentially, if you're the trick is, if you have a maximal ideal, then you know it is just allowing you to quotient out and take a functional which is actually a functional on the quotient. But this is one-dimensional, so the quotient of a space after an algebra over a maximal ideal is isomorphic to the complex domain. So that's kind of the principle of Gelfand-Mazur, which is coming into the game. And then you're playing around. I have to fix this. And so to make it short, if you're having a distribution which has this one-point support, that it's a multiple of a Dirac measure. If you're having a distribution which is supported on a lattice, you cut it into pieces, and it is sum over Dirac measures sitting at the lattice points. So maybe I will come back to this issue next time by telling you if you give me a distribution which is supported on a lattice and it's a mild distribution, it's nothing than a weighted sum of Diracs with a sequence of weights. So the lambda k are depending now on the points, which is uniform. So it's an L infinity sequence or so. Okay, we have spent much more time than I was expecting. So I will try to go quickly into MATLAB now and show you a few things which I have prepared already this time in the live script, and I will try to share it. So later on, I will tell you how I'm creating in MATLAB these partitions of unity, and it's a spline partition of unity, which means I'm convolving a function. The parameter n is the total signal length. The parameter a is telling you the shift parameter. So I'm shifting by multiples of 20. So they are centered at 0, 20, 40, or actually in MATLAB coordinates 1, 20, 1, 41. And then what I'm doing some smoothing. I'm convolving it with a rectangular function, and in this case, to get the ordinary B-spline, cubic B-splines, I'm doing it 3 times, so I'm convolving it 3 times, but now with L1 normalized rectangular functions, and the 3 is how many times I'm doing it. Now for me, because n equals 20, I have n over 20, which is 24 positions. So if you look up, you would count that I have 24 such building blocks. And I create a matrix which contains in the first row the first guy, in the second guy or so. I could add up all those rows, and that's why I prefer to plot to store this information in the row of a matrix. So it's a 24 times n matrix. The sum I could test. Yeah, maybe I don't do it here now. The sum would be just constant 1. Now to tell you the difference and how I was fabricating in the plot and also in mathematical ways, constructive description of these pupus that I was using. If I replace the same thing, I take the same A, but I take 3 and 5, it means I'm convolving 5 times with a very narrow rectangular function of width 3. So of course, if I convolve with a function with parameter 20, more or less you can say it's around the center symmetric, it's 10 plus, 10 minus. So the support will be of the triangular function is from minus 20 to plus 20. If I convolve it once more, it was like minus 40 to plus 40. Here it was saying I start with a rectangular function more or less from minus 10 to 10. Each time I'm convolving once more, so I'm doing 5 times the convolution. I'm adding only 3 pixels, so I have 5 times 3 is 15. 10 plus 15, it's only the foot here is only at 15. So I'm not changing too much, and that's why you see still here a plateau, and why I have to do the transpose command here. So I'm plotting the rows of a matrix, and the plot command in MATLAB is doing it with columns, so you see the partition of unity here. Now, one thing that I keep telling you is that the spline approximation with order 1, so we're doing only one convolution, and it's A and A here. So that's really B-spline. That's giving a triangular collection of triangular function. And this triangular function, as you see here, they are having the value 1/2 in the midpoint, so at half integers. That's clear because you go from, let's say if this would be 0, that would go from 1 down to 1 to 0, whereas the other one is increasing from 0 to 1, and so they're crossing exactly where each of them is contributing in the same way. So if we do the spline approximation operator for this guy here, we would sample a function, which means at these points, then we would put a multiple of this here, and that means I'm getting a piecewise linear function, and so we would do piecewise linear interpolation. The original B-spline, and I just here you can put anything because I do 0 times convolution, so I don't convolve at all. The starting point would be something that I don't have in my formal description, because it's just a rectangular function and they're not continuous. But of course, this is what you get if you do the deep psi operator on the measure mu. So think of a probability measure. If you integrate against this rectangular function, it's exactly what you get when you do the histogram. So it's not useless. It's B-splines of order 1 or degree 0. So the parameter here is more or less the degree. Now, another thing that I wanted to show, and I have now prepared it a little bit better, is when we do the Gabor stuff. So a Gabor collection is starting from an atom G, and in this case, G is already prepared to be a discrete Gaussian of length n. I'm doing shift parameters by multiples of A and frequency parameter shift by B. And my standard setting is that this is a signal of length 480, A equals 20, B equals 16. If you take the redundancy, that's n over A times B, it's 3 over 2, and that means we have 720 elements. And we hope and we expect, and it's true, that they will be a generating system for our signal space. And of course, what we are going for is to say, well, can we describe a given signal vector of length n as a linear combination of these things? Of course, we know that this is a discrete periodic setting. We could also say it's an ongoing periodic thing, and everything is taken in the periodic sense, but we take it as a localized version of something completely different. So like a piece of music. Now, what is the important thing is that we introduce the frame operator. I will do it formally a bit later, hopefully. And this operator is, we are doing first a scalar product, and then we are taking a linear combination. So G is a 720 by n matrix. So we have 720 row vectors. Because everything in my system is row vectors, we have to do right matrix multiplication. Imagine you have 2 row vectors, x and y, and you would like to get the scalar product. Of course, you're writing x multiplied matrix product with y prime. It's much more convenient than for column vectors, because for 2 column vectors, you would have to write y prime multiplied with x, and that's kind of switching order or so. But okay, but this is just my favorite way of doing it. That's explaining why this is an n by 720, with the 720 by n matrix. So this is an n by n matrix. So it's really an operator. This operator, of course, is describing the behavior of the frame matrix, the frame operator. And we essentially have to find out, and this is something I will do next time, hopefully, how to do the inversion of this frame matrix. But first we look at the diagonal. So the diagonal is just pulled out of this matrix by the diagonal command, and you see here. And that was kind of what I was finding quite important for the last 20 years. We were just implementing things in order to see what's going on. This was not done before much in Fourier analysis or so. And of course, you can see this is clearly a periodic function. So this is the diagonal part. And then the claim was, well, the verification is, it's a periodic version of the absolute value of that atom squared. So kind of, that's more to show you how I'm doing this. Well, if you have any Gauss function, you could look at the Gauss function, you could do the plot C command or so, then you would see that, maybe I can do it in between while I'm talking. I'm saying, well, let's look at the Gauss function and the squared Gauss function and see how they look like. What we do afterwards is just making it periodic. And not yet here. Yeah, here it is. So you see the Gauss function is made such that under the unitary Fourier transform, which is a discrete Fourier transform multiplied with 1 over square root of n to have the same amplitude. So this is really made such that it's Fourier invariant. I will explain also eventually how we do this. Then we take the pointwise square, which makes the Gauss function, of course, more narrow. And making things more narrow means on the Fourier transform side, you have a stretching. Of course, also the point value here is, the function is getting smaller, and therefore we have to look at the amplitudes. Okay, now the point is that I'm doing a periodic version. Sorry, maybe I go back to this command here, yeah. So how do I periodize? Periodization is a sum, it's a convolution with the Dirac comp. So I call SHA with SHAH is the Dirac comp, and A is our lattice. That's why I'm using this name. I simply do it in MATLAB, very half-line command. I put zeros and I put a 1 at all the lattice points, which are multiples of H. So I think of 0, 20, 40, but in MATLAB coordinates, it's of course 1, 21, 41, and it's ending up with 461 because 480 is too small and 481 is already the same as 0. Okay, so I'm doing this and I'm convolving this, which means I'm taking the Fourier transform of the compressed Gauss, of the squared Gauss function. I'm taking the Fourier transform of this Dirac comp. Well, I know it's a Dirac comp which has the value 24 because I have 24 spikes at the distance of n over 4 and n over a, and we have seen this is 480 by 20, so at a distance of 24, but that's not important. It's just this, and we multiply it, so we convolve it, and that's done by multiplying in a pointwise sense the Fourier transform, taking the inverse Fourier transform. Now, we have created G as a positive real valued function. The Dirac comp is taking values 0 and 1, and therefore, I'm not sure, yeah. Therefore, it's clear that the resulting convolution product will be non-negative. But in the computation, it may have a spurious imaginary part. So when I want to plot it, it's better, or compare it. Just take the real part to come back to the real domain anyway. And so I'm saying, well, now I'm not sure, is the normalization correct? And actually, it was not correct. It turned out that there was a factor, and then I was guessing what it could be. It turned out to be 30. So in the first command, so this command here tells me that they are equal. The size of the vectors is, the first one is bigger by a factor of 30 compared to the second one. But if you take the normalized versions of these vectors, they are equal up to numerical precision. So, okay, I'm saying, well, maybe this is n over b. Yes, this is n over b. Therefore, I'm multiplying the small guy with this missing factor. N is 480, b is 16. And I'm really showing that they are now equal length and equal. So it's just confirming the insight that the matrix that we get is not a random matrix. It's a matrix which is a periodic thing, and the window is used for analysis and synthesis. This is why it comes in twice and why we have this. So, well, what is the structure of this frame matrix? So later on, we will see it's a matrix, an operator which is commuting with certain time frequency shifts, but let's just inspect it. So I'm doing my spike command, but putting the 0 in the middle, and then I get this picture here. So it's looking like having some structures. It's looking like most of the information is on certain side diagonals, and we can count the number of side diagonals and so on and find out that we have, I think, B side diagonals. Yeah, B side diagonals. And if we look at the content of each of these side diagonals, it's always an aperiodic signal. Now, periodic is also maybe first before, this is the spice command. So it's a SPI command modified with the center in the middle. But then I was saying, well, this looks like numerical noise. Maybe, I mean, SPI itself says I'm making a red mark at any point where you have non-zero entry. So it's maybe better to look at the significant values that is giving us the second here. So you see here it's the main diagonal, which you have seen, and then there are some side diagonals. Now, of course, we could maybe, I just try to see if it works. I could control it and see if we get a different picture if we make it a little bit smaller. Or you could take a random atom, not a Gauss function, and then you would see that more of these side diagonals are occupied, but it's clearly a very well-structured matrix. Yeah, there's no change here. But with the random matrix, you would see that these matrices have this form. Now, for our MATLAB implementation, we were using this and say, well, why do you store an n by n matrix? We just describe it as a block. So each of these diagonal entries is periodic. So let's take the first A elements, because the rest is just a repetition. In other words, think of this not as a function of length n, but of length n over a. Then you're saying, well, but I need only to have this and the second side diagonal and the third side diagonal. And by the way, what is missing here, this side diagonal here is of course shorter. You should take it periodically. So you have this picture here, and then you're having a full period. So this is you store this part and you store maybe this part of length A, if this is fine, or maybe you continue it, or any representative. So in this case, I would store it in a block matrix of format A times B, and this turns out to be equivalent to the Janssen representation, which we will also discuss. So I would like to tell you, if you look at the matrices, you see something which is not a general matrix. You try to analyze it, and then you find out that you can use the structure and get good, fast algorithms to compute the dual Gabor atom or so. So one of my ideas, at that time a completely naive idea, was, well, if it's periodic, let's take a Fourier expansion. And this is just one of the Fourier images of the side diagonal. So instead of taking the Fourier coefficients, instead of storing the basic block of each of these n over b, which is n over b of these side diagonals, we take the Fourier coefficients of these. And we know that a periodic function has only a correspondingly small number of Fourier coefficients, which is kind of the inverse of this here, of the periodicity. And so it turned out that we can say, well, instead of having this, we have a Fourier version of the block description. Now, what is the unit matrix? If you would like to have a tight Gabor atom, which means you would like to have that your frame matrix is just the unit matrix. So you would like to have constant 1 here and 0 elsewhere. And so the story is, an atom has to be made such that these side diagonals are 0 due to the specific properties of the G, that the main diagonal is constant 1. And this is something I'm describing in the script meanwhile, how to fabricate it if you start with something which is not so good, how to get it by division, but I don't have to go into this detail anymore. But the story is that if you're starting with a function where this frame operator is invertible, then definitely the main diagonal has to be 0. And of course, if you would have constant 1, that would correspond to just one Fourier coefficient. Constant 1 is 1 times 0 frequency plus nothing else. And all these side diagonals have also 0 frequencies. So it means that you have just the identity operator should give you 1 coefficient in the Janssen representation. So I wanted to present this a little bit and saying that by inspecting the Fourier coefficients of these side diagonals, and we observe that there are few side diagonals, you're getting a very good intuition of how to handle these operators, how to maybe get a fast algorithm for inversion. And I think we should stop here. And thank you for your attention today. And see you next Thursday.